Okay. Okay, let's wait a couple of more minutes. Okay, let's get started. So last time I was not doing good job in explaining GIC, Generic Interrupt Controller. So let's back up a little bit and use this whiteboard to explain GIC. So at first it is a little bit confusing because there are so many registers in distributor and CPU interface, and this is a big picture. Okay? So actually it is not that hard because if you understand the function of GIC, this is a generic interrupt controller, the arm's name. And in GIC, you can have up to 1,000, 1,020, 1,020 IO devices. Basically, you can have in your system, you can have up to 1,020 IO devices, and each IO device goes by its unique ID. Because computer is processing ones and zeros, right? So you have to represent each IO device. For example, private timer that goes by with ID number 29. So now ID number 29 is representing private timer. Okay. And some interrupt from your custom logic. So that is inside PS, processing system in Jinx device. And inside the PL, probably you want to implement your custom IO device. Let's say that is Gpio. Gpio is implemented, so integrated inside the PL, and that is generated interrupt. Then probably you can connect that into GIC. Okay. And then you should connect that interrupt to ID starting from ID number 61. That is fixed. So if you look at the table, so ID is already fixed. You have to remember that. You don't have any choice. So if you look at this table, look at this. This slide. Where's the 20? SPI. This is SPI and PPI. Private timer. So ID is the 29. That is fixed. You don't have any choice. You have to use number 29 for private timer. Okay. And when it comes to custom logic, inside PL, KPL, and the ID start from 61 to 63. Okay, and this number, and also that number, PL. So 8. So if you look at this number, 68, 61. That means 8, right? 8 interrupt sources. 61 to 68 ID. So that can come from your customers, and also PL you have 91 to 84, another 8. Right? So some ID. So that can come from 84. the point is each I/O device has each ID. You have to remember. Okay. So in this the last demo we used private timer, and that is assigned this ID. 29 is ID for private timer. Okay. And then let's say the private timer is generating interrupt, your custom logic is generating interrupt. Then what you want to do? What you want to do is interrupt will be delivered through distributor and CPU interface, eventually go to CPU 0. CPU 0 will be interrupted, and what you want to do is CPU 0 in the middle of executing some program, right? Some, let's say it is hello world program. Then interrupt is generated. Whether it is timer interrupt, or Gpio interrupt, or USB interrupt. If you look at the table, there's a USB device, or some other I2C device. So these I/O devices can generate interrupt. Then what you want to do is eventually you want to execute interrupt service routine or timer. Okay. Timer interrupt ISR and interrupt service routine for GPIO. Right? There's a separate ISR and another separate ISR for USB, right? And ISR for I2C. So that is ISR, interrupt service routine. Okay. So depending on who generated the interrupt, you want to execute one of these four. Right? That is the goal. Right? That is the goal. Then let's talk about your distributor and CPU interface. When ARM architect designed this GIC, they had multi-processor in mind. So you can have up to 8 CPUs, 8 ARM CPUs in your system. So again, ARM is doing IP business, intellectual property business. So you get license, Samsung get license from ARM, then Samsung can customize. Okay, I don't need 8 your CPUs. I can use only, I need only 4 CPUs. You can customize it. Hynix license that IP. And okay, I need only two CPUs. I don't need another less 6. So same thing goes to distributor and CPU interface. Distributor was architected to support up to 1020 interrupt sources, I/O devices. Then when you license IP, then you can say, okay, I don't need 1020 I/O devices. I need only 96 I/O devices. I'm going to connect 96 I/O devices. That's a Zynq device. Okay, if you look at the table, okay, only 96 I/O devices are connected. So among these 1020, most of them not used, right? You use only 96 inputs. Okay? The point is, you get license, then you can customize because they are doing IP business, intellectual property business. Okay? So maximum you can have up to 1020 devices. So then, what is the function of distributor? As the name implies, right? Interrupt generated. Then you want to send that interrupt to one of these distribution. Which CPU? Which CPU you want to send that interrupt to? You want to send Gpio interrupt to CPU 0 or to CPU 7, right? Distribution. Right? For that purpose, distributor has a register called target register. Target register. That is 8-bit. Okay, 8-bit. Why 8-bit? Because you have 8 CPUs. You can have up to 8 CPUs. So 8-bit, and each bit is corresponding to 1 CPU. So bit 0, for example, is bit 0. Bit 0 is set to 1. Then that means, okay, I want to send GPIO interrupt to CPU 0. If that bit, the last bit, if the 7 is set to 1, then that means, okay, I want to send GPIO interrupt to CPU 7. Okay. So you have to program, target register. Who is the target? CPU 0 or CPU 7? Simple, right? But the thing is, because you can have up to 1020, you need 1020 target registers, right? So ID 0, this one, ID 1, this one, last one is usually set this. So one byte, one byte for each ID, each IO device. Does it make sense? So far so good. Okay. Then the thing is, because each register is 32-bit, 4 byte inside. I'll show you this map. Okay, distributor. Okay, so register map. So at the end, what you have to do is you have to touch those registers, right? You know the function of GIC, efficient and fast processing of interrupt, right? So at the end, you have to touch. What you have to do is you have to touch those registers with your program, right? So each register, control register, ID register, group register, each register is 4 byte in size. So we have target register. Okay, target register. Target register is here. It starts from base location. Distributor, right? Distributor starts from F8, F0. That is base F8, F0, then 1, 3 zeros. That is a base address, base location, memory map, right? Then actual target register start from that offset 800, right? 800. So start from 800. But the thing is, each register is 4 byte in size. That means it can hold. That each register can hold 4 is 4, right? So that this one is for ID number 0, that interrupt, and this byte is for ID number 1. Then third one, that's for ID number 2 and ID number 3. So one register can hold is 4 bytes. Right? So that location is offset 800. So this one plus the number. So F8, F0, 1, 800. So that register is holding this. So that is why it is a range, right? Target register, not just one, right? So you need to specify a target for these many inputs. So that is why you have how many? Start from 800, then ends with PF8. That is not good number to understand, right? But pretty complex. So for easy math, for simple math, let's say GIC can support up to 1024. Because we are familiar with the number, right? 2 to the power of 10. Right? So we are familiar with the number. So you divide, because each register can hold 4. So divide that guy by 4. Then you need 256 registers, target registers. You need 256 target registers, right? So last one, so there is 8-bit, right? 8. So 8 means what? So 8 registers and 1024 bytes, right? First byte, second byte, 1024 bytes. So 1024 bytes. So that means, that location plus what? 400 minus 4. 400. Why? 400 means in binary 1 0 0 4 zeros and another 4 zeros. So 10 bits. 1024. 2 to the power of 10. You can do some math, right? 2 to the power of 10. Or 4 ones and 1, or 10 bits are 1, then for rest. So you know this one. So do the math, then it's supposed to be what? This one is C00. But it starts from 0. Right? So you have to do minus 4. Then it's what? 0x PFC. PFC is the location of the last register. So we changed 1022, 1024. So one more minus 4. One more minus 4. That means PF8. That's why PF8. So so the thing is, you need many registers, and each register is holding 4 bytes, right? And with each byte, you can specify target for one input source. Simple, right? This byte for that ID, second byte for this ID, the rest of it. Okay? And that is a target register. And same thing goes to priority register. Priority in GIC assigned 1 byte to specify priority for each input. Same thing, right? 1 byte. Okay, 1 byte to specify target, and 1 byte to specify priority. So let's say this one. This 1 byte, okay, 1 byte is for that ID number, that IO device, and second byte is for specifying priority for that ID number 1. And then you have 1020 bytes you need, right, to specify priority for each. Then how many registers you need. Each register can hold 4 of them. So you can do some math. So you go to, you have this one, priority register, GICD, right? If the name starts with D, generic interrupt controller, and D, image distributor, right? This one. And CPU interface, GIC, and C, right? CPU interface, C. That's that. So priority, GICD, and priority register. You have many priority registers, right? Start from 400, offset 400. That is the base, and offset 400. Then 400 register can hold 4 bytes. 4 bytes. Then you can count how many registers you need to specify priority for 4 of them. So a little bit, simple math. It is like actually, kindergarten math actually, but a little bit confusing at first. Okay? So important thing is target register and priority register. Okay? You set priority for each ID, each IO device priority. Okay, priority register. And one more important thing is enable or disable. It is very simple. Right? Enable register. So enable register, let me use it. Enable. So there are two enablers, right? First one is global enable. Global enable and individual enable. Global enable and individual enable. The first register, that is global enable. Control, okay, just one bit. You can enable this distributor. Okay. That is the first one. GICD control register. So you have to enable, okay, distributor. Otherwise, the interrupt input will not be forwarded to CPU interface. You have to enable, right? Enable first. Obvious, right? And what do you mean by individual enable? Do you want to forward that ID number 0 to CPU interface? Individual, right? ID number 1 to CPU interface. ID number 5029 to that CPU interface. Then individual. Right? So you need one bit. Then I'm talking about this one. Set enable register. So register. Set enable. Set S enable register. And that is also 32-bit and each bit. 32-bit. Each bit is corresponding to enable or disable, right? So each ID, this ID. The first bit is corresponding to ID number 0. Second bit, ID number 1. The last bit, 32. So ID number 31. Then you can count how many registers you need to enable or 1020. So let's say 1024 for easiness, right? 1024 divided by 32. 32. Right? Then how many? You need 32. 32 registers, enable registers. Okay? To enable or disable individual inputs. Right? So if I do this, keep doing this. This one, second enable register. This one is for ID number 32, 31, 32. Okay? The last one, ID number 63. So on, right? So what is the offset? Enable starts from offset. This register offset 100. The next register, 4 byte, right? 32-bit, 4 byte. So simple 104. And so on. So then the last one is 17C. 17C is the last one. Can do simple next one. 0x 17C. Okay. So sorry, I think sorry. So we changed this number 1022 1024. So that means sorry 2 registers. But if you use original 1020, then 31 registers. You need only 31 registers to enable or disable. So so when it comes to private timer ID number 29, then which register you have to set? You have to use this register. Okay, and to enable private timer, enable means you want to forward that interrupt to CPU interface. Then you have to touch this register and which it. This one is for ID number 29 for private timer. Okay, so you have to touch that register and that specific bit. That specific bit to one enable. And also when it comes to target, right? Target register, you can do some math. Then you can find out which register you have to program to specify target for ID number 29. And same thing goes to priority. Which register you have to set. Okay, to specify priority. So let's do that. This one, first register is priority number 0 register. Let's say this one name priority number 0 register. And 29. Change that to 32, then 8. 8 means 7, right? Because we are counting from 0. So we have to touch what? Priority number 7 register. Okay, for that ID. Then priority number 7, you have 4 bytes, right? 4 bytes. That's priority number 7 register. Okay, so this one is for what? This one is for ID number. This one is for ID number 31. Okay, this one, sorry, and 29. So you have to program that 8-bit to specify priority for timer. Simple, right? You have to find out which one you have to touch, right? Based on that ID. That is the one. So if you look at the program, right? That's what I did, right? So check out. Enable first, right? Enable, I did 1 29-bit shift left. 29-bit shift left to find out that bit position. 29-bit bit position. Then one, then 29-bit shift left. Then did some OR operation. First I read, enable register and store it to R1. Then OR operation, right? R1, then R2. R2 is that first time. Then finally store instruction. The last one I want to check if that bit is set correctly by reading LDR, read from memory. I just want to check if that bit is set correctly. And priority, right? I want to program that priority 7 register, and that information is specified in this header file. Right, look at this header file, GIC priority, right? Started from priority 0, then 28, right? Priority 7. Base location F8, F0, 1, right? So priority register, I want to assign 10, right? 10. Any number is okay. Right? So what you have to remember is private timer. Private timer. Timer ID. It goes by with ID number 29. ID number 29. And then I want to set priority. Priority to that number. Any number is okay. Right? I chose that number. 10. In GIC, lower the number is lower number means higher priority. Higher priority. Lower the number is higher the priority in GIC. Okay. Anyway, I said priority to 10. That means here. Okay. Priority number 7 register. I set this one to 10. 1, 0. Okay. That is what I did right here. 10 and 8-bit shift. 8-bit shift left to find out find out the location, 8-bit shift. Then OR operation. Right? Then there is one. That is about distributor. So main function of distributor is what? You want to specify the target. The interrupt is generated, and that interrupt should be sent to which CPU? You have to set target and set up priority of individual input. Individual input. Okay, so ID number 0, I want to set priority 5. ID number 1, I want to set priority 10. ID number 2, I want to set priority 20. I don't know anything. Priority. ID number 10, 20, 10, 19. Set priority number F0. Anything. So set priority of individual inputs. Okay, priority register. That is the function of distributor. Okay, then that interrupt is generated. Then that interrupt will forward it to corresponding CPU interface module, hardware module, the distributor hardware module, and CPU interface hardware module. And each CPU has a dedicated CPU interface module. One module for CPU 0, another, this one is for CPU number 1, and the last one for CPU number 7. And in CPU interface, what you can do is you can set threshold, important register. We have to check this. That CPU interface, right? CPU purple 027, 027. So important register, you have to take a look. Is mask register. This one, mask PMR. Here, PMR priority. This one PMR means priority mask. Priority mask register. Yes. So that means what? That means you can set threshold. If you specify the priority, let's say, okay, I want to set, if you set priority to 20, set this one is a threshold. Threshold. That means I set timer interrupt priority to 10, right? So 10 is higher priority than this threshold. Lower the number, higher the priority. Lower, higher priority. So if timer interrupt is generated, then that will be forwarded to CPU interface, then that will be compared against the threshold. And this number is higher, right? Lower the number, higher priority. So that will be forwarded to CPU. What if the number is not 10, 30 timer interrupt? Then that will be compared against the threshold. The priority is lower than this threshold. So it will be masked, it will be blocked. This interface will not forward that interrupt to CPU. That is important function, right? Priority mask. And also the first register, control register, GICC, right? It starts with GICC, control, CPU interface. Control register is enabling. Enable, right? Enable that CPU interface. Right? So the same function as global enable. Global enable is enabling this whole distributor. And CPU interface, you have similar register for control register. Enable CPU interface. You have to enable it. And that is the thing you have to set, okay, before normal operation. So GIC, interrupt controller, is like special I/O device. You can think of it as a special I/O device. So when you do I/O programming, what did you do? I/O device has 3 kinds of registers: configuration, data register, and status register. Right? Before you use I/O device, you have to set up that I/O device configuration. Right? That is configuration. Right? Before you use GIC, set up priority register, target register, mask register, then normal operation. So it is like a special I/O device. GIC is also. Any questions so far? Yes. GPU를 포워딩하지 않겠다는 거죠.
원하는 수로 포워딩했다는 얘기.
So depending on your target setting, right? Depending on target. Let's say interrupt from GPIO, that is always forwarded to, let's say you design your custom IO device in ID number 61. And that target, let's say this one, target is, let's say this one is for ID number 61. And you specify, okay, one, only this one, 40. So that means that interrupt will be forwarded to only that interface. And then let's say GPIO priority is 30 priority. And that will be compared against the threshold 20. It turns out that this priority is lower than this threshold. That means CPU interface will not forward the interrupt. Ignore the interrupt, will not forward the CPU.
제가 좀 이해가 안 되는 건 이네이블과 디세이블이 있는데 스레시홀드라는 걸 가지고 블록킹한다는 게 이해가 안 돼요.
그 팔로시 enable disable은 인터럽트를 이제 인터럽트를 몇 가지 enable 그것도 enable disable의 종류라고 할 수 있어요. 그건 좀 그런데 enable disable은 각각을 먼저 enable 하겠다는 거. 들어오는 거를 일단은 받겠다는 거고 디스트리뷰터가 일단은 받잖아. 받아서 그 다음에 포워딩을 하는데 다음 단계로 그 다음에 여기서 이제 그 다음에 블락킹 메커니즘을 만드는 거지.
우리는 블록킹 했다가 풀었다가 블록킹 했다가 이렇게 유지를 했다라는
그렇지. 그거는 소프트웨어 아키텍트의 운영 방침에 따라서 내가 이 시스템을 어떻게 운영할지에 따라서 이 팔러스를 고치는 거죠. 나는 이거
운영을 못한다는 거면 펜딩 시켰다가 뭐 다시 리뷰하고 이런 서스펜드 리뷰 같은 경우가
그렇지. 그 인터럽트는 만약에 여기서 못 받았으면 처리 안 했으면 펜딩 돼 있는 거죠. 그래서 저기에 이제 또 보면 펜딩 레지스터가 있거든요. 디스트리뷰터에. 펜딩. 인터럽트가 지금 펜딩 돼 있다.
그걸 알고 있는.
그렇지. 그것도 그 정보도 여기 다 기록돼 있어. Okay, so take a look at so I have to take a look at specification, but there are pending, right? Clear pending, set pending. I think that is related to that pending, some pending register. Okay, so let's move on. So so far so good. That is initialization, right? Important register you have to set, right? Distributor and the CPU interface, right? And no more operation. Then interrupt happens. Then what you should do? What you have to do? Interrupt happens. Then the goal is I want to execute one of these four actual interrupt service routine. That is the goal. Assuming that there are only four interrupt. In ISR, according to the protocol, right? Interrupt is generated. You are supposed to refer to interrupt vector table. So there are 8 vectors, right? Branch, reset, branch, something, right? So based on that interrupt vector table, you are jumping to ISR, interrupt service routine. Not that interrupt service routine, but the central interrupt service routine, not individual interrupt service routine. Let's say branch IRQ, because we are talking about this IRQ interrupt. Let's say IRQ ISR, central interrupt service. That central ISR will check out something and jump to one of these four. Okay. So in central ISR, that is IRQ ISR. ISR. In IRQ ISR, what you have to do is you have to check out very important register in CPU interface. Here you have, let me remove. So crowded, let me remove. Here you have a super important register called Interrupt Acknowledge Register. IAR, right? IAR is second register. That is here. Interrupt Acknowledge Register. It says RO, right? Type is read only. Read only. Okay. You are not supposed to update, just to read that register. So what information is contained in IAR? It contains interrupt ID, IO device ID. If timer interrupt is generated and eventually forwarded to CPU, then IAR contains each ID 29. That will be recorded by hardware. Like 29. During runtime, right? I'm talking about runtime. 29 will be recorded by hardware. So what you have to do is you read in ISR, you read here, read IAR register, acknowledge register. Okay, read the register. Then you know, okay, by reading the register, you now know, right, who generated the interrupt. Okay, private timer generated the interrupt. So if the ID is 61, turn out to be 61, then your custom logic generated the interrupt. Then you can, by looking at this number, you can branch it to one of these four. Okay. So this one is important, right? So without interrupt controller, right? If you have just a simple OR gate between IO device and CPU, then to figure out who generated the interrupt, you have to poke around every IO device status register. But with that IAR, by reading just one register, you know, right, who generated it. You don't have to poke around. Okay, you did. You don't have to read status register from each IO device. So that will save your time, a lot of time, right? Interrupt latency, interrupt response time. Okay, that is a protocol. Okay, so you read this one, then at the end, right? So at the end, you are jumping to, let's say, this one. Then at the end, what you are supposed to do is write to end of interrupt register. End of interrupt register. This is the register. EOIR. That is, let's say, that is called write only. Write only, right? So you read I number 29. Right? If timer generated the interrupt, right? And then same number supposed to be written to EOIR. So you have here end of interrupt register. Okay. So after running your main function, some function you have to do, right? In ISR or time interrupt. At the end, you have to update that EOIR with the same number, 29. Then, CPU interface, okay, you are done. You are done processing timer. You are informing hardware, I'm done. Then CPU interface will prepare another, pending interrupt for the pending interrupt to the CPU. If let's say multiple, there are many devices are generating interrupt, and whoever has the next highest priority, that interrupt will be forwarded to CPU. If you write this register, that is a protocol you have to follow, right? Read IAR, then at the end you update EOIR, and I'm done processing. Then that guy will prepare next pending interrupt and send it to CPU. That is the protocol. So most interrupt controller has the acknowledge and end of interrupt. It's very similar function. So that is the beauty. By reading this idea, you know, to generate interrupt and informing this one, then this guy will prepare next interrupt to forward. And one thing you have to be careful is there is the protocol with interrupt controller, GIC. And one thing you have to be careful is for each IO device, right? Private time, if you remember private timer, countdown, right? Decrementing count, right? It has a status register. That is a sticky bit. Remember? That sticky bit will be set to 1 if countdown, right? Countdown to 0 happens. Right? Then what do you have to do? You have to clear that bit to 0 by software. Okay? How to clear? Writing 1, then clear it to 0. So before you write to EOIR register, you have to make sure for timer ISR. Okay, so write to status register in timer to clear the sticky bit. You have to inform that end of processing to each IO device. So inform here and inform here. EOIR. Inform to notify that to interrupt controller and notify that end of processing to that IO device. You have to be careful. This is not everything, right? You have to touch that interrupt generated IO device as well. Okay, that is why. So look at this. So interrupt processing, right? So here ISR. I'm reading, right? So there is ISR, right? I'm reading acknowledge register. I'm reading acknowledge register, and in this simple demo, I'm not doing anything with that ID. Simple example, right? I'm not doing this branch. I'm not doing this branch. Just read. Okay? And then in the main, I'm toggling LED, and at the end, look at this. There is no clear. Okay? Clear the sticky bit. Because timer generate timer interrupt. And inform generic interrupt controller. Inform generic interrupt controller. I'm done. Okay, by writing same ID. Okay. That is the standard procedure. Any question about this whole process? So a little bit confusing at first, right? But the main goal is what? Efficient and fast interrupt processing. That is the main goal. So how to implement that fast and efficient priority and target, right? And threshold and acknowledge and end of it register. Using that interrupt latency. The response time will be very super short. CPU can respond immediately, can process the final ISR, whatever it is, that will be processed. Any question? Okay, now let me. Okay, so one thing you have to cover is private timer. Private timer is you don't have to touch target register because each CPU has its own private timer. As a name, private, right? It is private. This one is private to CPU 0 and CPU 1. CPU number 1 that has also its own private timer. So in case of private timer, you don't have to specify target. That is already, the hardware already know. Right? That is hardwired to specificity. Okay? That is called. That is why private timer is called PPI in Zinc terminology. Private peripheral interrupt. Private IO, right? In other words, private peripheral, private I/O interrupt, private I/O interrupt, private peripheral, private I/O. But if I/O device, I/O your custom hardware, that hardware is shared. If some I/O devices are shared by shared with these 8 CPUs. In that case, you have to specify target. Okay, and so PPI, right? Private timer interrupt, and SPI, right? Shared I/O interrupt, and these are shared. The table, right? Those are shared. So this timer, the timer number 41, those are shared I/O devices and interrupts. Okay, so look at this PL. If you have a custom logic inside PL, and that is one of the SPI shared interrupt. Okay, so now let me design my custom logic. Okay, I want to generate the interrupt from switch on JET board. Okay, so let me show you from scratch. So what I want to do is I want to generate. If I press that button, there's a switch. We have a switch, right? If I press push up or down, then interrupt is generated. Here we have GPIO that is connected to that switch. That switch we can push up and down, right? So 8 switches. GPIO, your custom logic. If you push up or down, then interrupt will be generated that will be delivered through distributor, CPU interface, and finally the CPU. Let's do that. Okay. Let me show you a demo. So for that, you need to instantiate GPIO, right? And then open up that interrupt connection. Let me do that for you. Here, full screen. Let me do it from scratch, and that is this one, GPIO interrupt from PL ID number 61. Okay, I posted the reference design, but let me do it from scratch. Sit, open, Vivado. So this one will be very interesting lab, I think. Okay, project new. Hardware design, right? This one. So next, then let me put it into let's say class. I did that in the class. Design. Okay, select board. We are using JET board, right? JET. So next, finish. Okay, then create block design. Any name is okay. Okay, add. A PS processing system. We have a PS and PL section. It is suggesting run. Okay, do whatever you can do. Okay, so now instantiate a GPIO. Let's add 2 GPIOs, LED connection to JET board, right? And switch it 2 GPIOs, right? GPIO. And then that GPIO should be connected to, okay, let me copy and paste. Two GPIOs. Then before connection, I want to assign, okay, that output, GPIO output should be connected to LED. Okay. LED on Z port. Then that GPIO should be connected to switch. Okay. So before making connection, you specify that. Let's say this one. This one is LEDs. LEDs. This one name switches. Okay, then run connection automation. Right? Rely on Vivado. Okay, and Vivado will make connections. So that connection. Okay, switch, then LED. LED, that GPIO is output device, right? So I don't want to open interrupt connection, but switch is input device. You push up and down. Every time you push up and down, then interrupt. You want interrupt generated, right? So switch, then look at this. Enable interrupt. Okay, then you see, output port, right? Interrupt output is created. That physical output. Okay. Then PS supposed to have, because that GIC, right? That is GIC inside the PS, right? That open up that interrupt connection, you have to open up that input connection in GIC. To open input connection, double click. Double click. Okay, so here at the bottom in interrupt. Okay. So fabric interrupt. Fabric means FPGA, PL section, PL, programmable logic, field programmable logic, FPGA. So click, expand this probably. Click on this. See, then PL to PS. PL to PS. What is PL? Again, this is PL. You have a PL. Programmable logic PL to PS, right? PL to PS connection, interrupt connection. How wide that is? Let's see this. Check this. Then 16-bit connection. You can open up to, you see here. You can open up 16 input connection. Okay, and we are going to use just one 61. See? So open up this, then okay. Then see here, 0 to 0. Only one connection is created, input connection. So what you have to do is just connect using this. Make connection like this. Connect it. Okay. That's it. That is about hardware design. So save it. Then check something if everything is correct. Okay, no problem. Then what you have to do is standard procedure, right? You have to do what? HDL, top module generation, then generate bit stream. That's it. That is about hardware design. Okay, then you can click on this generate bit stream. That will take some time. Okay, so I already create project last night, and for demo, let me open up that same project. But before that, there is one more interesting thing. So remember, we used the logic analyzer before, right? You have a logic analyzer, right? You can connect the logic analyzer to the white breadboard, right? So physically, you can monitor what's going on physically on that wire by using logic analyzer. But about that, there's an internal logic that hardware design will be downloaded to PL section. That hardware design, FPGA, it will be downloaded. Then the question is, can you monitor that physical line amount internal line that is inside the PGA. So Xilinx is providing that capability, internal logic analyzer, not external logic analyzer you have, right? Internal logic analyzer. You can deploy internal logic analyzer. It's very simple process. What you can do is you can click on this wire. Then I want to monitor that right click on it. I want to monitor. Look at this debug. Just want to monitor that. Okay, debug. Then tool will look at it. Is suggesting connection automation, right? Tool will implement that logic analyzer for you. Look at this ILA. System ILA, integrated logic analyzer to monitor internal wire, internal wire. So let me do this. Okay, so look at this module. This one is connected. Interrupt line is connected to this ILA module, and clock is connected also to ILA module. So you know that hardware mechanism is very similar. Every clock cycle, every clock cycle that ILA is sampling. Okay, we have integrated logic analyzer. You have clock input and the interrupt, right? Interrupt wire is connected. So you have interrupt. Okay. So clock is running like this, right? It's running very fast, and interrupt is generated. Then every rising edge of the clock, that ILA will store that input. Okay. Let's say the line looks like this. Then this one INT. Then at this rising edge, it's stored. Okay, 0. Okay, at the next rising edge, okay, it is 0. Okay, rising edge, it is 1. Okay, 1. Okay, and so on. So that information will be pulled out to your computer, and it shows waveform. It shows that kind of waveform on your computer screen. Okay. So stored information will be sent to your PC. 0011, right? 0001, something like this. Waveform will be displayed on your screen. Okay. So that is the project. Let me open. Okay, let me open. So recent project I did last night. Gpio Interrupt. Open project. No. Okay, so Gpio, not class, right? Gpio Interrupt, then open block design. Same hardware design. So you have ILA, right? LED and switch, right? LED and switch have connected through Gpio. Okay, then this interrupt. Gpio is generating interrupt that is connected to PS, right? And that goes to ILA as well. Okay, so I already generated bit stream. Then let me open IDE ByteS. This one launch. But the problem is I cannot do the demo here. I have to go to my office to push up and down. So someone needs to help, right? Someone, can you please come down here? And I have to open up the Zoom session there and display that. Okay. So that is the one. Okay, that is the one. And the thing is, here, the same register setting. So we are using interrupt ID number 61, and you need to find out which register you have to program to set priority for ID number 61. Okay? And target also, in this case, target is important because it is shared interrupt. So I have to specify, okay, that interrupt should be sent to only execution CPU10. Okay. Then why is it so small? Okay. And then okay, okay, we are running out of time. So let me show you a demo and I come back. Okay. So here, so that is the one. Let me show you one thing. So look at this. ID number 61, right? That is why enable, right? Enable register. That enable register. Okay. So offset 100, in case of private interrupt, private timer, I set this one. In case of GPIO, which bit, which register you have to set. ID number 61. So that means 63, 62, 61. That bit should be set to 1 to enable. So that means that is why I did that. 61 minus 2, right? There is 29. 29 bit shift left to find out that location. And do same operation and target. Get this target register. And you need to find out there are many target registers for each ID. So we have to find out which ID to program for ID number 69. And that is the one target. Target 15.5. Okay, then in ISR, what I'm doing is, okay. So I said I left this timer. It is nothing. It has nothing to do with that demo timer setting. Don't worry about that. And ISR, I'm reading acknowledge register, okay, and toggle LED. Then end of interrupt register programming. And before that, GPIO status clear. Okay. So let me show you a demo. Then come back to you. Okay. What is to do? Someone can you hear me? So you have to. So that is broadcasted, right? So exit Zoom session, and I share my screen. That will be displayed here. Okay, can you guys hear me? Someone, can you hear me? Hello? Hello? Can you hear me?
Can you hear me? Can you hear me? No, you cannot. Okay, great. Okay, let me download this these two, the board. Is it correct? Okay, correct. Okay, then let me set breakpoint here. Set into this one, the interrupt vector table, right? So let me let it go. Then it will do what? It will set up, right? It will set up, it will set up GIC here, generic interrupt controller. Okay, and then what? Then private timer, again, it has nothing to do with this demo. Don't worry about this. This one, private timer read, don't worry about this. It is executing forever loop. Okay, so keep executing this one. Then when I press the button, when I push up and down, then interrupt hopefully will be generated. So let me keep running, and I set breakpoint here, so it will stop here. Okay, let me press 8. Then let me press the button. Let me push up. Hopefully. Okay, stopped here, right? Somehow. Okay, stopped here, right? Breakpoint. Then it will jump to. It will jump to here. Look at this. Acknowledge register, right? Where is that? Okay, it's too big. So if you read the acknowledge register, F5, then R3, right? Then 61 will be stored, right? Because that interrupt ID is 61, right? 5, 61, right? See? Six one, right? 61. Then LED toggle. Right? Take a look at this LED, right? LED is turned on. Okay. Then end of interrupt, then return back to the place. So forever loop, right? So let me remove that breakpoint. So every time I push up or down, okay, switch that LED will be turned on and off. Let me press F8. Then every time I do this, interrupt is generated, and I touched something. Okay, I did something wrong. Okay, let me do it again. Okay, so it is sensitive to the shock. Please, shoot, please relaunch. Okay, it is sensitive to the shock, so I have to be careful. Okay, let it go, F8. Then every time I touch something. Okay, So let me show you a demo next time. So it is sensitive. Okay. So let me come back then.
Every time, then LED will be toggled. So that is it. And you can monitor that your toggle with ILA. I can show you this waveform next time. Okay, that's it. That's it for today. 당연하지. 디바이스 만드는 사람이 소프트웨어 만드는 사람이 컴퓨터 시스템에서 하드웨어하고 소프트웨어 있잖아. 펌웨어 만드는 사람들이 이 I/O 디바이스를 위한 I/O 사이트를 만들어놔요. 기능이 다 다르잖아. I/O 장치의 기능이 다르기 때문에 당연히 있어야지.
저희 인베리드가 하는데 디바이스 제대로 만들었어요. 저 개수가 몇 번?
1010개까지 I/O 장치가 있었어요.
저런 거 있어요.
근데 저거는 이제 IP를 제공을 하니까 자이링스에서 IP를 만들 때 1020개까지만 달 수 있다는 거죠. 근데 그 정도면 충분하잖아. I/O 장치 1020개면. 근데 그걸 라이센스 받는 회사에서 이제 자기가 결정하는 거지. 아, 너무 많아. 그중에서 나는 10개만 사용할게. 결정할 수 있는 거지. 커스터마이즈.